This is Anchi from the University of Utah talking to us about, I assume, cache coherence.
Okay, right. So modern chips combine multiple processors to run workloads efficiently. So for example, the NVIDIA Grace Hopper chip uses a CPU and GPU with shared memory between them. So each device's coherence protocol is glued to the others through this global coherent interconnect. So like CXL, Chai, NVLink C2C, and in Grace Hopper it is NVLink C2C. And that gluing is what lets the two devices share memory. So when a CPU-GPU program is compiled for such a chip, the CPU and GPU code are typically compiled independently, each with their own mature compiler, and all the communication between the two devices goes through shared memory, supported by hardware protocols. And independent compilation relies on these protocols composing directly. Now, to see what this shared memory communication looks like, consider a simple CPU-GPU litmus test. So initially, all values are 0, and the CPU writes a 1 to a data object, and then next, in the preserved program order, sets a flag to signal that the data is ready. And here, preserved program order means that the CPU memory model guarantees the writes are not reordered. And then on the GPU side, the GPU reads the flag with an acquire, and if the flag is set, reads the data. So the expectation is that the GPU sees the new value and not the stale 0. So, and because these two sides are compiled independently, this only works if the CPU's ordering rules play well with the GPU's. Now, if the hardware has glued to the two sides correctly, then the GPU's acquire reads from the external CPU and from the flag, and then observes that it's set. And once that flag is observed set, the ordered data read after it must read from the external CPU right to the data. So it cannot observe a stale value of 0. So all of this hinges on one thing, that the hardware correctly glues the CPU and GPU together so that the device's preserved program order is preserved in the fused system. The notion of the heterogeneous correctness in this system was recently formalized as the compound memory model. And in short, today's practice of independent compilation rests on the CPU and GPU playing well together. And that playing well together is what exactly compound memory consistency is. So achieving compound consistency is tricky. The hardware has to be carefully designed to enforce it, and getting it right is subtle even on commercial silicon. So if we take the Apple M1 as an example, it supports 2 memory model modes, 1, a TSO mode, and 2, an ARM mode, and each of its preserved program orders and communication relations are of TSO and ARM. So when we run the same litmus test with one thread in TSO mode and the other in ARM mode, each thread independently obeys its own model, but the composition does not respect the ARM TSO model, and the litmus test is violated. But in the single modes where it's just TSO and ARM, they are not violated. But here, in this mixed mode, the data legally can read a stale value of 0, even when the acquire reads a 1 for that freshly set flag. So this forbidden cycle is allowed. And we have conveyed this result to Apple, and we are not claiming it's a bug. TSO mode is an undocumented feature intended for x86 emulation, and Apple has confirmed it is not meant for cross-mode shared memory synchronization. The point is simply that achieving correctness in a heterogeneous setting is difficult. So ideally, these compilers and programs for these chips should just work unchanged. So in other words, we want the system to satisfy the compound memory consistency model, the CMCM. And to achieve the compound memory model, designers have to apply this de facto standard. They add these translation shims between each processor's coherence protocol and the global interconnect. And when a memory operation propagates within a cluster, the shim intercepts it and synchronously propagates it to the other devices as well. And the synchronous propagation rule is used extensively in academic designs and appears to be used in industry as well. The question is it correct? And in this work, we show that it is. Synchronous propagation already correctly enforces the compound memory consistency model, and the result is general. It applies to a broad class of CPU and GPU style protocols in use today. So specifically, as long as the individual CPU and GPU protocols satisfy the properties we describe and prescribe, the global interconnect satisfies the single writer multiple reader invariant, SWMR, enforced by protocols such as CXL and Chai. Then synchronous propagation guarantees this compound memory model. And This work therefore provides this formal foundation for heterogeneous shared memory today. Furthermore, the result enables a composition approach to verification. Designers only need to verify each individual protocol against the properties that we mandate and check that the global protocol satisfies SWMR. Our compositional proof, 26,000 lines of lean, then does the heavy lifting and shows that the composed system enforces the compound memory model. So there's a huge variety of coherence protocols across CPUs, GPUs, and other accelerators. And our theorem has to hold for them all of them. So the hard part is that CPU and GPU protocols are fundamentally different. In CPU protocols, a writer eagerly invalidates the other sharer's copies. And in GPU protocols, it deliberately avoids this writer initiated invalidation. And instead, it can cache or write back data, and upon a release, then write back, and it will self-invalidate other caches upon an inquire. And a moment ago, we said that our result holds for any protocol satisfying these properties that we prescribe, but how can one set of properties span protocols this different? That is a central challenge. So how do we reason uniformly about this plethora of protocols? So let's understand how these protocols work using the same message passing example. So here we have two CPU cores, each with their own cache, holding both data and flag in the shared state with initial value 0. And when the core 1 writes the data, it sends this invalidation that removes core's 2 copy of the data. And then when it writes the flag, it likewise invalidates core 2's copy of flag. And then later, when core 2 reads from the flag, it misses in its local cache and fetches the up-to-date value, and the same for data. So this is SWMR, this writer-initiated invalidation behavior. A write will eagerly invalidate the other sharers, so stale copies cannot linger. The GPU, however, as we'll see next, takes a very different approach to coherence. So in contrast, a GPU protocol works very differently. So consider two CPU cores, both caching flag and data locally with value 0. When core 1 writes to data, it will simply update its local cache. It does not need to send any invalidation to core 2. So at this instant, core 2 still holds its local stale value of 0. And then when core 1 does a release on the flag, it will write back that dirty data to the shared LLC, and then it'll write back its flag to the LLC. And then when core 2 reads from the flag with an acquire, it'll bypass its cache, grab that fresh value from the LLC, and then self-invalidate its local cache. So then its subsequent access for the read will miss and then fetch the new data from the LLC. Right. Now, consider a combined CPU and GPU system. The key players are the shims that connect the CPU protocol and GPU protocol to the global protocol. And again, assume that the flag and data are cached both locally in the CPU and GPU with values of 0. So when the CPU writes data value 1, then it sends this request to the directory, and the shim will then intercept the message and then synchronously propagate it into the global protocol as a global invalidation, and then and then the local write does not complete until that global step does. So the global invalidation needs to reach the GPU, invalidate the copy of the data in the GPU's LLC, but not change its local cache. And the write of flag to 1 does the same thing, invalidating the GPU's copy of the LLC of flag. Now, when the GPU performs an acquire, it bypasses and self-invalidates its local cache and goes to the LLC. The shim intercepts that miss and synchronously issues a global coherence request, which causes a flag held in CPU's 1 cache to be forwarded. And then the subsequent read value of the data likewise misses and is forwarded to the CPU. So how do we reason about the correctness of all of this? And in particular, how does it satisfy compound coherence and consistencies? Yeah. So our key idea is this unifying abstraction for coherence protocols, one in which we can express all of these very different protocols. And the abstraction has to walk a thin line, be rich enough to express every protocol, yet abstract enough that we can reason about correctness uniformly across all of them. So to that end, we present 3 ideas. So first, linearization points. This is the point at which a coherence protocol makes a memory operation visible. And as we'll see, we distinguish between local and global visibility. Second, abstract states. This is a uniform way to capture a cache holding sufficient permissions to satisfy an operation locally as a silent hit without further communication, whether it's a GPU or CPU cache. And finally, consistency labels. Each operation carries a label, its ordering contract, which is how we relate behavior of the coherence protocol, the consistency model it must enforce. So let's see these three ideas in action and go back to the litmus test we explored. So concerning the CPU writing data, it misses and is sent to the cluster directory. And at that point, that's where the shim intercepts it. And the synchronous propagation rule propagates it to the global protocol. And here in this global step, this is specifically synchronous. So this global operation is encapsulated by the local request. And so the global linearization has to finish before the local operation completes. And then for two CPU writes, sort of something like a data and then flag, both are serialized across the cluster directory in that order. And because each global step is encapsulated within the local requests, the global linearizations occur in the same order. So in other words, when the local linearization occurs, it is carried over to the global order, and that is exactly what preserves the CPU's local order globally. So now for the harder case, where both data and flag are already held in modified state in the CPU's cache. So when we run the same litmus test again, but now with the two writes being silent hits, so they have permissions, no request reaches the cluster directory. So there's nothing for the shim to intercept. So how is this propagated globally? And that's where the abstract states come in. We can mark both blocks as write coherent, and the key point being here that the cache can only reach this write coherent state by having earlier acquired the line through the directory via synchronous propagation, the global protocol. So the cache state is a cached proof that the global linearization has already happened where the line was brought in. So this is where the previous slide's global step happens now, but here in this case it happened earlier. And the abstract state records this fact. And because the global protocol is SWMR, no other cache holds these blocks. So any later read anywhere on the chip is forwarded on to this cache. And we'll see the correct value. Right. So the final piece is the consistency labels, through which we capture the ordering guarantees the coherence interface provides, effectively attaching an ordering contract to each request. So CPU protocols, for example, carry SC read and SC write labels because they enforce SC at the coherence level. More importantly, or specifically, this is the consistency model at the coherence level, not the architectural one. So any SC enforcing coherence protocol can still realize a weaker architectural model like TSO, ARM, or RISC-V through pipeline reordering. GPU protocols in the same vein carry acquire read and release write labels. And by attaching these labels to coherence requests, we can reason about the consistency effects of a coherence protocol, and that is exactly what connects the coherence to compound consistency that we set out to try to prove and enforce. Right. So is our abstraction just a toy, or can it express realistic protocols? And it can. So on the SWMR side, it can express the MOSI family, so CXL cache protocol, ARM AMBA-CHI, and on the GPU protocol, it can span anything from simple write-through self-invalidating protocols to, in the style of these commercial GPUs, up to advanced ownership-based protocols like de novo from academia. So we're able to model all their behaviors as axioms. And we don't just express them. To make this concrete, we model-check these two protocols end-to-end against our axioms, so CXL cache, an industrial protocol, and de novo, an advanced academic protocol, and both of them are instances of our abstraction. So we prove that, okay, for any P1, P2, protocol 1, protocol 2 that satisfies our axioms, that satisfies the SWMR properties or RCC properties, they'll compose so long as the global interconnect satisfies SWMR. So then the composed system will satisfy this compound memory model. And this entire proof is on lean and it's available. And what makes it useful in practice is that a designer only has to verify that their individual protocols satisfy our axioms. Our theorem then guarantees that the composition is correct by construction. So in summary, today's heterogeneous shared memory systems, such as Grace Hopper and others, run independently compiled code that rests on an unstated assumption that machine satisfies compound consistency. And how do we get to compound consistency? Here too, the field has relied on an unverified rule, and that is synchronous propagation. In this work, we prove that this rule is correct and machine checked in lean. So our result does two things. It places heterogeneous shared memory on a formal foundation and enables compositional verification of future hardware, where you just have to simply verify that each protocol locally satisfies the axioms, and the composition is then given by correct by construction. It took decades for homogeneous machines to get to the formal consistency foundations, and heterogeneous machines don't have to repeat that history. Right, that's it.
While the next speaker is setting up, we'll have time for just about one quick question. Well, I have a quick question then. Sometimes I see heterogeneous clusters that actually don't have globally coherent caches or otherwise have old or unreliable hardware that participate in it. Does your compositionality result extend to those clusters and say something about the residual coherent component of the cluster actually will have guarantees? Or does the presence of non-coherent hardware break everything?
Okay, so specifically if there is no coherence protocol on the device.
I'm saying I have like an old style hybrid supercomputer where I have some non-coherent memory and some coherent memory. The coherent memory has a similar interconnect to what you're describing, but the non-coherent memory also exists. Do your results say anything about the coherent portion of my system, or does the presence of the non-coherent portion invalidate your assumptions?
Okay, so it doesn't. So the proof doesn't directly handle that, but the proof framework does extend to this kind of system. So long as you have some primitives or axioms that you can describe to reason about those non-coherent actions, then you can incorporate them and make them work with the proof framework to show that there's some kind of compositional model with that.
Great. Let's thank the speaker one last time.